So welcome to the last lecture. And here's a reminder on oriented matroids. So here's the definition of circuits of an oriented matroid. So there's a bunch of simple axioms, and the last one is the elimination. We have two circuits which have an edge in the opposite directions. Then you can eliminate that edge and find another circuit. And then basically, for a given set of circuits, you can define covectors and cocircuits, which basically covectors are just all things which are orthogonal to circuits, where orthogonal means something kind of slightly weird. Here's the definition. And cocircuits are the minimal by inclusion covectors. And what I think I mentioned last time was that last time I mentioned that the circuits of the dual oriented matroid are just by definition equal to the cocircuits of your original matroid. So if you have any oriented matroid, you can look at the cocircuits, and there are going to be circuits that are going to satisfy these axioms for some other oriented matroid M star, the dual. So now this is duality. So okay, now for usual matroids, we had some duality statement, which like for realizable unoriented matroids, what was the duality? If you have a bunch of vectors, I give you a bunch of vectors. How do I find the dual oriented or the dual usual unoriented matroid for such a configuration? Right. Okay. I look at all bases and then I take the complement. But geometrically, what do I do? All right. So here is the answer. What I do is I take a matrix. Well, I take the row span from the matrix with columns v1, etc., up to vn. As this is a d by n matrix. I take the row span, so I get an element of the Grassmannian. Right. Do you remember that? Or and then I do transpose. No, actually, well, not. If I do transpose, I get an n by d matrix. Yeah, there's a trick. I have to like choose an identity matrix here and then take the transpose of what remains. Or in other words, I just take the orthogonal complement of this linear sub. This is a linear d-dimensional subspace of R to the n. So I take the dual, and this is going to be kind of n minus d by, this is the row span of another matrix, which is n minus d by d dimensional by n dimensional. And the point is that if you look at the column vectors of this matrix and take the corresponding oriented matroid, the corresponding usual matroid, the usual matroid for U, dual is equal to the matroid for its orthogonal complement. That was the statement for unoriented matroid. How do I how do I upgrade this to work for oriented matroids? Let's say, for instance, if I start with the same vector configuration, I could form an unoriented matroid from here, or I can form an oriented matroid. These vectors, if I look at the signs of minimal linear dependencies, they're going to give me circuits of an oriented matroid. This gives me an oriented matroid. Okay, now now if I do the same thing, I take the row span of such a matrix. We had some claim that the unoriented matroid is invariant under row operation. So what happens to the oriented matroid? Is it also invariant, or does it depend on the if I apply row operations, is it going to change? Okay, so I could, some signs are going to, of some determinants, yeah, I could change the sign of all determinants. But actually, if you remember, applying these row operations just corresponds to some sort of global linear transformation on all these column vectors. And this matroid records linear dependencies between these vectors. Right? And so the linear dependencies between them actually are unchanged. If I apply global linear transformation to the whole collection of vectors, the linear dependencies are going to stay the same. So actually, the oriented matroid of V still depends only on U, not on the choice of this matrix. And so it's denoted M sub U. And in particular, I can apply the same machinery, right? I still take the orthogonal complement and then look at the corresponding oriented matroid here, which is, so here I have to choose a matrix, but the actual oriented matroid does not depend on the matrix. And so the proposition here is that the dual oriented matroid of U is the oriented matroid of U perp, the orthogonal complement. So this duality actually, so that, by the way, unoriented matroid duality was only, it only worked over, it worked over arbitrary fields, right? But for oriented matroids, so all this stuff is only over R. I have to talk about signs of coefficients of linear dependencies. So yeah, here the ground field is always R. Yeah, but anyways, the point is that this duality, which is sort of complicated, right? You have to take these orthogonal complements and then take minimal vectors. That's still the same operation on the Grassmannian, just orthogonal complement. All right. And while I'm here, so remember, let's see what do you remember. So the Grassmannian, say K or maybe D, and over R, so let me fix the field to be R, was the union of over usual matroid, right, of these cells, X sub M. Remember that certification? Did it have good properties or bad properties? Topologically, bad properties, bad topology. Okay, but now we can upgrade this, right? We can, instead of looking at arbitrary, at unoriented matroids, I can actually take the same Grassmannian over reals, and I can write it as a union over oriented matroid. where the oriented matroid stratum is just the set of all U's inside the Grassmannian, which have this prescribed oriented matroid. Right? So in a sense, for every oriented matroid, you can look at the underlying matroid. And in particular, kind of this certification here refines that certification there. So what do you think? Are these pieces going to have good topology or bad topology? Bad. Why? Still bad? That's your guess. Okay. Yeah, that's actually true. So again, super bad topology. Basically, so previously, again, this is due to Minov. Previously, we had like here, these could be as bad as any algebraic variety. Here you get as bad as any semi-algebraic variety. So you can get polynomial equalities as well as inequalities. Still very, very bad. And if you here, some of these cells are going to be empty, right? If the matroid is not realizable over R, the stratum is going to be empty. And similarly here, some oriented matroids are not realizable over R, so some cells are going to be empty. And it's another kind of feature of this certification is that it's intractable. It's a very hard intractable problem to tell which oriented matroids are realizable. So this picture is very sad, and hopefully, oh, by the way, there is another negative. No. Well, I spent a while talking about that polynomials for matroids, characteristic polynomials of hyperplane arrangements. So you might wonder, do you get any new information from the oriented, by orienting your? And the answer is that no. At least we don't know any. At least I don't know any known extension of that polynomial or characteristic polynomial to the oriented picture. Anyways, so these are all very negative results, but hopefully, if I have time left, not sure, hopefully there's going to be a happy end. There's going to be something very pleasing at the end, but maybe not. I'm not sure. Yeah. For now, any questions on this stuff? Yeah. Yeah, I think that could happen. Yeah, you could have non-realizable over R oriented matroids whose underlying matroids are realized. Yeah. So by the way, there's another hard problem. If I give you an unoriented matroid, there's a question of whether it's orientable or not. That's also hard. Yeah, does it come from some oriented matroid? Sometimes it doesn't, and it's hard to tell which ones. So yeah, everything is very hard. All right. Any other questions? All right. Back to zonotopes. Let's say I have a vector configuration. And let's say I look at the corresponding oriented matroid. And let's say I look at the corresponding zonotope, which is the Minkowski sum of these line segments. In this case, it would actually be more natural to take this from negative V1 to V1 and negative Vn to Vn. But let me just take from 0, because that's easier to draw, actually. So if you remember how we tried to describe these like faces of the zonotope, right? What's a face? From each line segment, you either choose one endpoint or the other endpoint or the whole line segment. So how do you describe them properly? You use sign vectors. Sign vectors have pluses and minuses and zeros. So yeah, if you have a sign vector, let's say my ground set is just bracket n. And then if I have a sign vector c plus c minus, then plus minus 0 to the e, then I can define the corresponding, I'm going to call it f sub c, is just so for each plus, I take the right endpoint, for each minus, I take the left endpoint, and for each 0, I take the whole line segment. Basically my definition. So it's the sum over I in C plus of Vi plus the sum over J in, let me say that C0 is E minus the support of C. So E without C plus and C minus. J in C0 of whole line segment. Okay, and I am like, the ones in C minus I just don't take because the left endpoint is 0. Okay, and now here's the question. Which sign vector, if I take the zonotope and I look at its faces, which sign vectors do I get? Let me even try to draw a picture. So let's say I take the corresponding vector configuration, V1, V2, V3 parallel to V4. And then let's say I take the corresponding zonotope. That's my zonotope. And that's the origin. So if I can you tell me what's the sign vector that labels, let's say, this face? 1, 2, 3, 4. 0, minus, minus, minus. Okay, yeah, that's actually correct. How about this one? Minus, wait, hold on. Plus 0, minus, minus. And these two vectors actually form a single face. So what's it going to be? Plus, plus, 0, 0. And then the rest are like negatives. Okay. So I wonder if anybody can guess what are these particular. Yeah, let me even draw. So the negatives are going to be 0, plus, 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 and then minus 0, plus, plus, and then minus, minus, 0, 0. And I can even go further, and I mean, I can consider lower dimensional faces. Like, for example, this vertex here. What's the sign vector here? Plus, plus, minus, minus. Nice. And what about this one? All pluses. Plus, 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 plus. Okay. So I should look at this picture and I should see these sign vectors. What's the word for them? So the map, yeah, I'm going to start writing the proposition while you're guessing. The map C to F sub C is a bijection between anybody? Sign circuits of what? Okay, let's see. So, for example, here there's a sign circuit of let's see, what are this? Yeah, that's actually interesting. So what are the circuits of my matroid here? Like for example, 1, 2, 3, 4, plus minus 0, 0 is a circuit. But it never appears. Yeah, that's close, but covectors. Interesting. Yeah, these are all covectors. What is a covector? You choose some hyperplane, and then you look which vectors are on which side of that hyperplane. Like if I draw a hyperplane here, and 2, 3, 4 are going to be plus, and 1 is going to be 0. So that's this guy. And if I draw this hyperplane, then 1 and 2 are going to be plus, and these 3 and 4 are going to be 0. That's this guy. And if I draw some generic, maybe like a hyperplane like this, then I'm going to get all pluses, etc. So this map is a bijection between, indeed, covectors of M and all faces of my zonotope. And if I want facets, then I get, what do I take for facets? Right. So yeah, but these are actually co-circuits. Yeah, these are, when you have as many zeros as possible, that's a co-circuit. Right. Absolutely. Yeah. So beautifully, these kind of very natural notions for this oriented matroid describe the faces of the zonotope. And that's cool, but let's say maybe I choose some zonotopal tiling of this. And then each of these tiles, right? Remember, in the zonotopal tiling still, this is the Minkowski sum of some of these vectors shifted by some other of these vectors. So each of these tiles actually gives me a sign vector. So my next question the next question is which collections of sign vectors give me zonotopal tilings? Question. And that's actually, yeah, this one, I'm not expecting you to guess this one. But let's first motivate. Like, what happens if I'm interested only in regular zonotopal tilings? For regular zonotopal tiling, what you do is you lift every vector, lift each vector to R d plus 1 dimension up. And then you take the corresponding zonotope. These, I have d plus 1 dimensional vectors, I take the corresponding zonotope. And finally, I project lower faces, this lifted zonotope back to my original zonotope. Okay, now if I want non-regular tilings, what do I like? How do I generalize this to my matroidal language? Well, let me actually tell you how to do that. So here's the definition: a lifting of a given oriented matroid. Let's assume that the ground set is just equal to bracket n, because that's happens in our examples. The lifting of this oriented matroid is an oriented matroid m prime on ground set bracket n plus 1, such that if I contract n plus 1, get my original oriented matroid. So as you may remember, right, from in the last lecture, we discussed contraction. And contraction corresponds to basically, yeah, let me try to draw the picture. So the picture is that your original matroid M, maybe it comes from vector configuration like this: v1, v2, v3, and then M comes from V. And then what's ellipting? I have to add another vector, such that if I contract that vector, I get my original matroid. Well, what is contraction of these vectors? What does contraction mean geometrically? Right, yeah, that's correct. So indeed, contraction for, I explained this for unoriented matroids, but it's the same for oriented. You just project all vectors onto their orthogonal complement. So if I take these two vectors and let me try to draw them like this, and then I put them one dimension up. So I add another vector, v4, yeah, let me call it v4 prime. Yeah, the prime vectors are going to belong to this primed oriented matrix. So I add another vector so that if you project, I recover these two vectors. And then I have to lift, yeah, maybe I lift, maybe I keep v1 and v3 here, but for v2, this is v2, maybe I choose some other representative. Like v2 prime, something like this. And if I project everything back to my hyperplane, I get my original vector. And in particular, you see that basically if this M prime matroid is realizable, then this is basically the definition of a regular, well, of at least, this is the same as step 1 in this procedure. You just lift every vector one dimension up. But this matroid can be non-realizable. Then there wouldn't be a picture corresponding to it. But you could still kind of lift, there's still kind of an extension of these regular tilings. So yeah, but then I'm supposed to take lower faces of the corresponding lifted zonotope. What are these lower faces? Yeah, so the puzzle here is that even though this M prime matroid may be non-realizable, so there could be no actual zonotope in d+1 dimension. The lower faces are, I mean, first of all, the faces of that zonotope they have a matroidal description. The faces of the zonotope are just covectors of my matroid. So in particular, if I have a lifting of my original matroid M, then I'm going to define the corresponding tiling defined by M prime to be the set of all these spaces. The f sub c is defined over here. F sub c, where c is a sign vector supported on n, such that c comma minus is a covector of m prime. So what this means is that basically this extra minus sign is the n plus 1, n plus first coordinate of my covector. And so anyways, the meaning of this, if m prime is realizable, then this is the same as saying that this is a lower space of z tilde, of the lifted zonotope. If it's not realizable, then it's just something else. And any questions so far? Is it clear what I'm doing, or is it completely? All right, let me assume that it's clear. Yeah, I'm almost done with this. Yeah, let me just state a theorem. So the theorem, which is due to Bon and Dress, is that this is a bijection. If you take any lifting and you take the corresponding collection of faces like this, P of m prime, this map is a bijection between liftings of m so if you're given a vector configuration, you take the corresponding oriented matroid, and then you look at all possible liftings. And the claim is that you get all possible zonotopal tilings and all zonotopal tilings of m, of the corresponding zonotope. So yeah, let me try a simple example. Let's say I take a vector configuration which looks like this: v1, v2, v3. Let's say I take the corresponding zonotope, and let's say I choose some zonotopal tiling. And here's the origin, and then yeah, maybe you can tell me what's the sign vector for this tile here. Zero, zero, minus. And what about this one? Minus 0, 0. This one, 0 plus 0. Okay, so what does the theorem tell us? The theorem tells us that if I look at these sign vectors, then these are the lower faces. Or if I add a minus to them, I get covectors of my lifting. So, and actually, if I only look at the top dimensional tiles, then I'm going to get cocircuits of my lifting. So these cocircuits of the corresponding lifting of my matroid are, I take all these vectors, minus 0, 0, minus, 0, 0, minus, minus. I just add a minus to all of them. 0 plus 0 minus. And then I take their negatives, plus 0, 0, plus, 0, 0, plus, plus, 0 plus, 0 plus, or 0 minus, 0 plus. And then there's going to be some more, because there could be other covectors which have 0 in this coordinate. There's actually some other covectors. And the claim is that this is a lifting of my original matroid. And the actual lifting, actually, the picture, did I erase? No, the picture looks like this. Let's say I look at this picture, and I try to compute the covectors of this picture. Let's see. Here I have minus 0, 0, minus. So I want a hyperplane where v1 and v4 are minus, and v2 and v3 are plus. And that's actually, if I draw a hyperplane through v2 and v3, the other two vectors are going to be on top of, on one side of that hyperplane. And similarly, yeah, you can check that all of these sign vectors are actually covectors of that picture. So, but if I drew a non-realizable, some sort of non-stretchable tiling here, it would correspond to a non-realizable matroid. So yeah, let me actually write this down. So in this correspondence, this is a bijection between all matroids and all liftings and all tilings. In particular, M prime is realizable if and only if the corresponding tiling is regular. And you can also explain, like, it's easy to explain when it's fine and when it's not fine. Yeah, these are all zonotopal tilings. And, okay, so why did I rush to explain this theorem to you? Well, I mean, I like this theorem, but that's not quite enough. The actual reason is because so far everything we did so far, like the Tod polynomial, you could define it for realizable matroids, like for actual vector configurations. And you would never have to go out of the world of realizable things. And similarly, whatever the characteristic polynomial, all the hyperplane arrangements, those are all realizable. So why would you introduce matroids if you could just stick to vector configuration? And actually, so this is an example why. Let's say you want to study zonotopes. You want to study zonotopal tilings. If you only want to study regular tilings, then it's fine. You can think of in geometric terms. But if you want to study all zonotopal tilings, then those are just in bijection with all matroids which are liftings of my origin. And there's no other, like, there's no actual geometric way to describe these zonotopal tilings without introducing matroids. So that's one reason. And another reason is that I had to, I mean, I promised you a bunch of stuff at the beginning of the class. Let's see. I think in the first lecture, I drew a diagram of what was going to be in this class. And the diagram looked like this. There is going to be, you start with a vector configuration, and then you may take the convex hull, so you get a polytope, or you can take Minkowski sum of line segments, and then you're going to get a zonotope. Or you can take orthogonal complements, and you get a hyperplane arrangement. Or you could look at the basis, and then you get a matroid. Or you can look at oriented circuits, and then you get oriented matroid. All right, and then there's also graphs, and there's also directed graphs. If you start with the graph, you can look at the graphical zonotope, or the graphical hyperplane arrangement, or graphical matroid. If you take a directed graph, you get oriented matroids. And then I drew a bunch of arrows between these objects. So you remember, polytopes are dual to themselves, and zonotopes are dual to hyperplane arrangements, and matroids are dual to themselves. Oriented matroids are dual to themselves, and graphs, I asked you what they are dual to, and you had no idea. And the same for directed graphs. And now, hopefully, you actually know all these dualities. I think I explained all of these dualities in the class. And also, I drew more arrows. For example, polytopes are zonotopes are polytopes, and etc. And oriented matroids, there is this arrow is that theorem over there. Oriented matroids describe all zonotopal tilings and faces of zonotopes and etc. And then there was an arrow, matroids, like the lattice of flats, describes hyperplane arrangements and etc. And also, I guess I didn't explain this arrow between oriented matroids and hyperplane arrangements. But anyways, you can get the matroid from any oriented matroid. Anyways, almost all these arrows, I think I ended up explaining. And that's why I needed that theorem to complete the picture. And I think I have 10 minutes left. Any questions so far? Okay, that's a good question. So there is a theorem that every oriented matroid, let's say you take a central hyperplane arrangement. Let's draw a picture. Something like this. Central origin. Then intersect it with a sphere. So you get a big sphere, and then each hyperplane is going to give you a smaller sphere. If you intersect each hyperplane with a sphere, you get a smaller sphere. So you get an arrangement of spheres of codimension 1 inside the big sphere. And there is a theorem that oriented matroids are arrangements of pseudospheres. So you should think of oriented matroids as some kind of stretchable pseudoline arrangements, non-stretchable. You should think of this picture as being drawn on a sphere, and then each pseudo-line as being like a smaller sphere in a big sphere. And there is a theorem that all oriented matroids are deformations of hyperplane arrangements. Each hyperplane arrangement gives you an oriented matroid, but to get all oriented matroids, you just kind of allow to bend your hyperplanes in some prescribed topological way, and you get all oriented matroids. So these oriented matroids actually do correspond to pictures. But those pictures are kind of topological. They are bended in some way. Any other questions? Cographs. Well, usually the graphs and cographs are nice. Well, cographical matroids are a very nice class of matroids, which you can prove a lot of stuff about. But it's because of the duality, everything you can prove for cographical matroids, there's a dual statement for graphical matroids. So they're as nice as graphs. Any other questions? All right. I want to end on a positive, still end on a positive note. So here is a positive bonus. The bonus is the totally non-negative Grassmannian. Which is defined as follows. You take all elements in the Grassmannian, this is the row span of a K by N matrix. And then you look at so the condition to belong to the totally non-negative Grassmannian is that all maximal minors are non-negative. Okay. So I want to define a subset of the whole Grassmannian. The whole Grassmannian is stratified into matroids in an intractable way. Now I take a subset of the Grassmannian where I only take matrices with non-negative minors. And you can restrict to the same stratification. You can look at matroid stratification. probably non-negative Grassmannian. Well, it's over R. It's certified, so you can take, again, all matroids. Now you can look at these restrictions. You can only look at elements in here which have the prescribed matroid. Right? And then you can ask, what is the topology of the strata? And what's the answer? Great, contractible. What else? How good are they? Duality complex. Give me more. How many balls? Yeah, you can tell exactly which ones appear in the certification, which ones given an empty cell. Yeah, actually, yeah. Let me. You're very. Yeah, you're guessing. You're all guessing correct. So, well, nicest possible topology. What do I mean by nicest possible topology? Yeah, let me know by figuring 0. So each cell, each non-empty cell is actually an open ball. So not just contractible, but an open ball topologically. And if you take the closure, you get a closed ball. And that's, this theorem is easy, and this theorem is super hard. It used to be an open problem for like 15 years. And basically, yeah, it's what is called a regular CW complex. And it's, again, it's very easy to tell which ones are realizable or not. So yeah, there's a lot of recent research on that stuff. And so I guess that's where I'm going to end the class. Any questions or?